Large language models translate every single text prompt into precise mathematical coordinates within a vast, dark landscape of numbers. This environment is the latent space. It is a mathematical manifold, a complex geometric landscape where the exact meaning of a concept is defined by its physical location relative to everything else in the model's world. This visualization plots thousands of handwritten digits from 0 to 9. Based purely on visual characteristics, the model maps the data so that similar shapes naturally cluster into distinct, localized neighborhoods. While we perceive these clusters in 3 dimensions, the underlying model operates in a space of 768 dimensions or higher. Understanding these systems requires a look at how they generate these coordinates, how we sculpt the high-dimensional space using contrastive learning, and how we mathematically compress those dimensions to observe the results. Interpreting modern artificial intelligence requires observing it as a topological structure. Every word enters the model as a static token, a fixed list of 768 numbers serving as a baseline lookup vector. These static vectors are rigid, lacking the situational geometry needed to distinguish if the word data refers to a field of science or a specific character in a story. The model addresses this through the self-attention mechanism, an engine calculating how much each word should influence the representation of its neighbors. The vector transforms into 3 pathways: query, key, and value. Multiplying the query and key generates an attention score, measuring the precise relevance between words. Multiplying this score against the value pathway bakes the context into the vector, shifting its spatial position. This context-weighted coordinate then passes into a multi-layer perceptron, or MLP. The MLP is a feed-forward neural network that refines the features of each token independently. The MLP projects the coordinate outward into a much larger space, often expanding from 768 dimensions to 3072. This expansion allows the network to capture complex, nonlinear patterns that were previously hidden. After extracting these refined patterns, the model mathematically compresses the vector back down to its original 768 dimensions, ready for the next layer. The transformer block effectively acts as a coordinate calculator, moving a token's physical position in the latent space based on its relationship to its neighbors. With these coordinates plotted, we face an engineering challenge, identifying a mathematical way to determine if 2 data points are truly similar. Engineers use cosine similarity, which measures the angle between 2 vectors rather than their physical distance. It is invariant to scalar magnitude. Vectors pointing in the exact same direction carry a 0-degree angle and are considered semantically identical, regardless of length. Using standard Euclidean distance, measuring a straight line from one endpoint to another, would incorrectly classify these 2 aligned vectors as distant and unrelated. In a recommendation system, the length of a vector often represents interaction frequency, such as how often a user clicks. We measure the angle to ensure the volume of clicks does not mask the user's actual preferences. In high-dimensional environments, semantic identity is defined by direction, while magnitude often represents noise. General-purpose models often fail on domain-specific data, such as proprietary technical logs or enterprise manuals, where they lack the nuance to group related concepts together. We resolve this using contrastive loss. This training method mathematically pulls documents containing the correct answer closer to the query, while pushing irrelevant documents away. Engineers use hard negative mining to sharpen the model's gradients. A 95% margin filter around the target document scans for hard negatives, documents the model perceives as relevant but are actually incorrect. Penalizing the model for these near misses creates a mathematical repulsion, restructuring the space. Training only against easy negatives, obvious garbage data, provides no useful signal for a model to learn the subtle boundaries of a professional domain. Multi-hop unrolling further refines this by ensuring that complex prompts requiring information from multiple documents pull every relevant source into the query's orbit. Fine-tuning operates as geometric engineering, forcing the manifold to physically map the nuances of the data. Humans cannot perceive 768 dimensions. To evaluate these structures, we must mathematically compress the data down to 2 or 3 dimensions. The algorithm T-SNE is a common choice for this, though it often destroys global topological relationships while preserving local clusters. This woolly mammoth skeleton serves as a benchmark for dimensionality reduction. Preserving the macrostructure of this complex point cloud when flattening it requires a more advanced tool called UMAP. UMAP constructs a fuzzy simplicial complex, a weighted graph that calculates the likelihood of points being connected based on their high-dimensional proximity. To prevent isolated clusters, UMAP calculates a local radius for every point based on the distance to its nth nearest neighbor. The visual result changes based on two key parameters. Increasing n neighbors forces UMAP to prioritize the broad, global structure of the data over fine details, while the minimum distance parameter determines how tightly the points pack together in the projection. Because UMAP distorts space to achieve this projection, the size of a cluster and the distance between groups are topological guides, not literal measurements of semantic gap. These projections are invaluable for identifying patterns, but they are lossy translations of a much deeper mathematical reality. This journey moves from a static word to a context-baked coordinate, and finally to a domain-sculpted manifold. The transformer block executes the initial movement, shifting token positions based on their neighbors. Cosine similarity provides the compass to navigate that space by measuring the angles of semantic intent. Hard negative mining terraforms the environment, ensuring the manifold respects the boundaries of specific knowledge. And UMAP compresses the result, making high-dimensional logic perceptible to the human eye. Engineers treat embeddings as manageable geometric structures, replacing the concept of the black box with precise mathematical control. Mastery of artificial intelligence is the mastery of the geometry of meaning.